everyone again. Welcome back to mahasarkar.co.in. In this article, we are going to learn about theorem of perpendicular axis. In a previous article, we have learned theorem of parallel axis and one of its application, so that you can understand what is the requirement of learning these two theorems. Now, in this theorem, we are going to deal with only plane laminar bodies, like any notebook, any plane surface of any shape. So, there will be three axes, such that one axis will be perpendicular to the plane and second axis will be parallel along the plane. For example, it's suppose a plane laminar body, and say this red marker now indicates that this is the axis of rotation which is perpendicular. This is the axis of rotation perpendicular to the surface. Okay. Second axis, so this notebook may be suppose rotating around this axis like that. Now second axis is say like passing like this, means notebook may be rotating in this manner. Okay, and notebook may be rotated in this manner also. So these are three axes. The first axis is perpendicular one, second axis and third axis. Okay, all three are parallel as you can see. Okay, all three are what? Parallel. Now, moment of inertia of axis perpendicular to plane, means this one, is equals to sum of moment of inertia of these two axes that we are going to prove. To prove this, basic definitions we are going to use, but we should clear that all three axes are concurrent to each other and they are combining at point O. Okay, so to study moment of inertia, say it is x-axis, this one is x-axis, say this is y-axis and this is z-axis, x-axis, y-axis and z-axis. So moment of inertia of that body about z-axis is equals to sum of moment of inertia about x-axis and y-axis, that we are going to prove. As now you can see they all are perpendicular, and if I take any point here, so that point will be also perpendicular. Okay, so the triangle drawn here in the diagram is also a right angle triangle. Okay, so let's prove that. What we are going to prove is, we are going to prove IZ is equals to Ix plus Iy. Remember, z axis is perpendicular to the plane surface and x and y are along the surface. This we are going to prove. Now to prove, consider any point P, consider a particle of mass dm at point P as shown in figure here. Now say from z axis perpendicular distance of that particle is r, from y axis perpendicular distance is x, and from x axis perpendicular distance is what? Y. Okay, now by definition mi of particle about z axis can be given by formula. That particle has distance r and mass dm, so I can write it is r square into dm by definition of moment of inertia. So if I want to use mi of body about z axis, then it will be like Iz is equals to integral of r square dm. Can we write similarly for y-axis and x-axis? So I can write also mi of body about x-axis. Now see, this is x-axis, perpendicular distance is y. I am writing for body, not for particle directly. So I will write, therefore moment of inertia is Ix is equals to integral y square dm, and mi of body about y-axis. So now as you can see, for distance y-axis distance is x, therefore I suffix y is equals to integral of x square dm. These are three basic equations that what we needed to prove this theorem. Now proof of this theorem is very simple. See, I already told this is the right angle triangle. So in right angled triangle, ONP or OMP, anyone, using Pythagoras theorem, what we can write? OP square is equals to ON square plus PN square, ON square plus PN square equal to OP square is nothing but R square, ON is Y, so it is Y square, plus Pn is what? X square. Multiply both sides by dm, multiplying both sides by dm, what we are going to get? R square into dm equal to y square into dm plus x square into dm. On integrating both sides, we'll get integral r square dm is equals to integral y square dm. I have already separated the integration x square dm. Just see equation 1, 2 and 3. What is LHS? LHS is nothing but I suffix z is equals to, what is this value? From equation 2 it is Ix and this will be what? Iy. So we have proven this theorem. We call it as what? Perpendicular axis theorem. This theorem also has unique applications to find the moment of inertia of this ring-like material. So let's learn those also. Let's find moment of inertia of ring about it any diameter. So red and this black both represents moment of inertia about the ring about its diameter. Like this, it is going to rotate. Whereas if this is the ring, moment of inertia about passing through its center is given by formula mr square. So we want to find out, say, instead of writing, say this is x axis, this is y axis and this is what? Z axis. Then by perpendicular axis theorem, I can say that moment of inertia about z axis can be equal to moment of inertia about x axis plus moment of inertia about y axis for that ring. But we know that diameter axis for the ring will be same, so moment of inertia about x axis is equals to what? Y axis. But here Ix is equals to, say, Iy, and say it is equals to moment of inertia about diameter. So therefore we can write mi of ring about any diameter, this should not be, can be written or can be obtained as, say, Iz is equals to id plus id becomes 2id. Therefore id can be equal to Iz upon 2. Value of Iz is what? mr square upon 2. So moment of inertia of that ring about any diametrical axis can be given by formula mr square upon 2. So in a such way one can apply the application of perpendicular theorem so that we can understand moment of inertia for different positions for different objects. I hope you understood this. Thanks for watching mahasarkar.co.in. Have a nice day.